This is the fourth installment for chapter 10 or part 4, and we are going to look at testing of hypothesis for the difference between two population proportions. So in much the same way that we are sometimes interested in whether or not there's a difference between two population means, we can be interested in whether or not there's a difference between two population proportions. And so let's take a look at what we have. We have a question that we're going to deal with about gender differences in terms of raise or promotion expectations, and whether or not there's a difference between the proportion of women who feel that they will get a pay raise or a promotion versus men. And so that's an interesting sociological problem to kind of look at, right? Okay, so before we get into that, let me just quickly recap the formulas that we would use if we want to do a confidence interval problem and if we wanted to do a hypothesis testing problem. All right, so I'll come back to the question very shortly. So here's what we're looking at. If we are interested in P1 minus P2, hypothesizing about the difference between population proportions. And so if we want a confidence interval, so a 1 minus alpha times 100% confidence interval, so confidence interval, here we go, interval for P1 minus P2 would be given by P bar 1 sample, right? Always remember that, the point estimate, plus or minus. And of course, we always do the normal approximation to the binomial, so it would be z. And we use our sample values that we have, which is p bar 1, 1 minus p bar 1 over n1 plus p bar 2 times 1 minus p bar 2 over n2. All right? So you may recall that in the single sample case, we had the standard error of p bar was p1 minus p times 1 minus p over that, right? The square root of that. Well, now what we have to do is we have to put the two variances on the inside. We have to put the two variances on the inside, add them, and then take the square root. Okay? So let's put that over this side right here. So that's our confidence interval formula. What's our test statistic formula? I'm going to just shift over to this page right here so we can see better. So if we are now testing for a hypothesis for the difference between P1 and P2, our test statistic will look like this. Z is equal to, and in our null hypothesis, we're going to assume that HO P1 minus P2 is either greater than or less than or equal to 0. I'm putting all three there. It could be either equal to 0, greater than or equal to 0, less than or equal to 0. But we have, the important thing is that we have 0 in the null hypothesis. If we have 0 in the null hypothesis, when we go to do the test, it would mean that P1 is equal to P2, right? So if that is the case, then we have to do something interesting. Our test statistic should look like this, right? Sample minus the population, P1 minus P2, which in this case would be 0. And then in the denominator, we need the standard error, which would be P1, 1 minus P1 over N1 plus P2, 1 minus P2 over N2. But we have a problem. And what's our problem? Our problem is that we don't know P1 and P2. All we know is that they're equal and the difference is 0. So since we don't know P1 and P2, what should we do? Should we use the sample estimates? Now, if we decided to use the sample estimates, and obviously we won't know the population proportions, because if we did, we don't have to hypothesize about it. So should we go with the samples? But here's the situation. We have a similar situation to what we had with the variances. When we assume population variances are equal, the two samples that we get more than likely will not be equal. So it's the same situation here where we assume in the population proportions would be equal based on a null hypothesis that says the difference is 0. However, our sample proportions will not be equal to each other. So we cannot use the individual sample proportions because they will not be the same. So what we have to do is we have to replace it. And we replace it as follows. We will remove the index and find a value p bar, where p bar is a pooled sample proportion. Remember we had pooled sample variance? Now we have in pooled sample proportion. So we'll actually calculate p bar by pooling the information from the two samples and getting a single estimate. So from sample 1, we would have counted x1, right? And then sample 2 would have counted x2. That is the number of observations. And then we just simply combine the two sample sizes and we get a value p bar is equal to x1 plus x2 over n1 plus n2. Now, if we don't have the actual number of observations, or we have a sample proportions, that is also equivalent to n1 times p bar 1 plus n2 times p bar 2 over n1 plus n2. So either of those would do, right? If we actually have the amounts that we use to calculate our proportions, then fantastic, we use this one. But if all we have is a sample, n1 and a p bar 1, n2 and a p bar 2, but we don't know the actual numbers, or we're not given those, then we just use n1 times p bar 1 and n2 times p bar 2. I'm sure you could understand that a sample proportion, right, is the number of observations x over n. If I do the cross multiplication, x is just n times the sample proportion. So all I'm doing here when I say n1 times p bar 1, that's just x1. And n2 times p bar 2 is just x2. Right? In other words, the number of observations. So those two things are equivalent. All right? So just keep that in mind. So we have the test statistic when in the null hypothesis, we assume the population proportions are the same. We have another situation, and you will notice that there are two test statistics when it comes to proportions. So if now in HO, P1 minus P2 greater than or equal to, or less than or equal to, is either greater than some particular value or less than some particular value or not equal to some particular value, not equal to, sorry, or equal to a particular value, where that value V is not 0. If that's the case, then clearly P1 is not equal to P2. And our best estimates of them will just be our sample estimates, P bar 1 and P bar 2. So in that case, we would end up having a test statistic that look like this. P bar 1 minus P bar 2 minus P1 minus P2. And that P1 minus P2 will get its value up here, right? That V, whatever that value is. And then, of course, we will use the individual sample proportions. P bar 1 times 1 minus P bar 1 over N1, P bar 2 times 1 minus P bar 2 over N2. So that will be our test statistic, all right? And I will give you, we're going to work a problem right now where you will get to see both of those being applied. All right, good. So let's go back to our problem now, our problem context. So we have gender differences in raise or pay promotion expectations. The Adecco Workplace Insights Survey sampled men and women workers and asked if they expected to get a raise or promotion this year. Suppose that the survey sampled 200 men and 200 women. If 104 of the men said yes and 74 of the women replied yes, are the results statistically significant in that you can conclude a greater proportion of men are expected to get a raise or promotion? So we have state the hypothesis, what is the sample proportion for men, for women, and then use a 1% level of significance, what is the p-value, what's your conclusion? Essentially, it's just asking you to find. It's asking you to find, oh, it's not find, but to do a hypothesis test, okay? So I'm going to merge all of those into a single problem, which is basically, I'm going to do two things. First, I'm going to actually find a confidence interval for the difference between the proportion of men and women who who are expecting promotion or a raise, and then I will repeat that as a hypothesis test, okay? And then I'll also do the third situation, or I should say the second hypothesis situation, where in the null hypothesis, we do not assume that the difference between the two proportions is actually zero. So let's go here. So here's what we got. Let's put our data down. We're going to let 1 be men, only because the sample proportion is going to be higher for men, and 2 be women. And I like to take a smaller value from a bigger value. So therefore, P1 is the proportion of men who feel they will get a promotion. P2 will be the proportion of women who feel they'll get a promotion or a raise. We have also data that says we have a sample size, both N1 and N2 are 200. And then we have X1, the number of men who said that they will get a raise, it was 104. And then X2, the number of women was 74. So from that, we could calculate our sample proportions, X bar 1, which is 104 over 200. And that gives us 0.52. And then P bar 2 for women, sample proportion, is 74 over 200. And that's 0.37. So already just from the sample statistics, you could see that a higher proportion of men thinks that they will get a promotion, 52% versus 37% of women. Okay, so now let's find a confidence interval. We're going to use the data and we're going to do our own thing. So let's find a 98% confidence interval. A 98% confidence interval for P1 minus P2, that's the difference between the two proportions, is given by, and so our formula would be P bar 1 minus P bar 2, that's the sample estimate, plus or minus Z. And then, of course, our standard error, P bar 1 times 1 minus P bar 1 over N1, P bar 2, 1 minus P bar 2 over N2, all right? So that's what we have. Let's just substitute the values and see what we get. So we have 0.52 minus 0.37. And for 98% confidence interval, Z is 2.33. By now we should know that. And then we'd put P bar 1, we said was 0.52. So 1 minus 0.52 gives us 0.48 over 200 plus 0.37. 1 minus 0.37 gives us 0.63 over 200. All right, that's what we got. So now let's actually figure out what that is. It turns out that this part, which is the standard error, is 0.0491. And then we have the 2.33. So when we multiply those together, the point estimate of the difference is 0.15 plus or minus 2.33 times 0.0491 gives us 0.15 plus or minus 0.1145. All right. Let us now summarize the confidence interval. So adding and subtracting, we will get P1 minus P2, the confidence interval, is somewhere between, when we add the 0.1145 to 0.15, we'll get 0.2645. When we subtract it, we get 0.0355. So when you look at that difference, we are 98% confident that somewhere between 3.55%, that the difference between the proportion of men and women who believe that they'll get promotion, all right, is between 3.55% and 26.45%. All right, that's a pretty wide interval. I'm sure you'll agree with that. So we are looking at, yeah, that's, there you go. So according to our results, we do have evidence. We do have evidence that more men than women feel that they will get a promotion. Because look, the difference between them is somewhere between 3.55% and 26.45%. So we are 98% confident. We are 98% confident. The difference between the proportion of men and women who feel that they will get promotion or pay raise, the difference between the population proportion of men and women who feel they will receive promotion or pay raise is between 3.55% and 26.45%. And any value in that interval is positive. So we have evidence that more men than women, right? So that's evidence that more men than women are expecting a pay raise. All right? So that's our result just based on doing a 98% confidence interval. We're now going to do a hypothesis test to see if there's a difference between the proportions, but not if there's a difference, if more men than women actually feel that they will get a promotion. So we have completed a confidence interval problem. Now we're going to do a hypothesis testing problem. All right. So let's set up hypothesis tests. So the question essentially is there sufficient evidence that more men than women feel they will get a promotion? Is there sufficient evidence okay, let me just I think for some reason, there we go. Sufficient evidence that more men than women expect to get a pay raise or promotion. So, hypotheses, step one, HO, HA. So, it's a fairly long statement of a hypothesis. So, we will say here, more men expect to be promoted, expect pay increase or promotion, and the same or fewer men, the same or fewer men expect pay raise or promotion. So if that's the case, HOHA, if more men expect, then P1 minus P2 will be greater than 0. And then if the same or fewer, P1 minus P2 will be less than or equal to 0. Okay? So that's what we have here. Now let's get a test statistic for that. Now you see how there's 0 in the null hypothesis. So that means that when we do the boundary test and we set P1 minus P2 equal to 0, that means P1 is equal to P2. So in this situation, we could call that case 1. P1 will be equal to P2, is equal to some value P, which we'll estimate by P bar. Okay? So 2 test statistic. And we would have Z is equal to P bar 1 minus P bar 2 minus 0 in this case because P1 minus P2 will be 0 from the null hypothesis, but that's okay. We will just, when we're ready, and then we will do P bar 1 minus P bar over N plus P bar 1 minus P bar over N2. So over N1 and N2. And the reason for that, we have to use the pooled sample proportion, P bar, because we don't know P1 and P2. And since in a null hypothesis we are suggesting that they are equal, we cannot use P bar 1 and P bar 2 because those are more than likely going to be different. And then just to remind you that P bar is obtained by x1 plus x2 over n1 plus n2. We are pooling the data from the two samples. So it's called a pooled sample proportion, just like the pooled sample variance that we did earlier. So that's step 2. Let's move that over here. Some space. Step 3. The decision rule. So this is a one-tailed test because we want to find evidence that P1 is greater than P2. So if I do that, let's use a different color. Okay. So we have the following. And I'm seeing here that something slowed down here. I'm not sure, a little glitch. All right. System is getting slow. We will reject HO right here. So this is alpha. We're going to still use we're going to still use I think no, the question is asking us for a 1%, 0.01. So that's 0.01. That is actually still 2.33. All right, rejecting the hypothesis. So if z is greater than 2.33, we will reject the null hypothesis. Otherwise, we fail to reject it. Let's do step 4. So step 4, analysis. We have z is equal to p bar 1 minus p bar 2, which we know already was 0.37, but I'll put it down, 0.52 minus 0.37, sorry, which we already knew was 0.15, minus 0. This comes from the null hypothesis, remember? And then, so in case you wonder where the 0 comes from, here, okay? The null hypothesis. Then the standard error, which we know is 0.52 times 0.48 over 200 plus 0.37 times 0.63 over 200. Okay? So things are getting a little slow on my end right here. Hopefully I could finish this up before it conks out on me. Okay. So it turns out that this value, when you do all your computation, is equal to 3.02. 3.02. Since this is a one-tailed test, our p-value is just equal to probability of z greater than 3.02, and it turns out that that is 0.0013. 0.0013. So now we have our p-value, and we have our test statistic. We know our critical value is 2.33, so we are exceeding that. So we clearly will have evidence to support us. Now, where do I put this? Ooh, sorry. My. I don't know what happened here. Let's see. All of a sudden, I got a whole whack of Let's solve this. Let's deal with this issue here. Okay, here's where we are. It's crazy. All right, so we will finish this up. Step 5. Decision conclusion. The decision conclusion, so we could say since 3.02 is greater than 2.33, we will reject the null hypothesis. All right? What's our conclusion? Oh, we could also look at the p-value as well. The p-value is 0.0013, which is less than 0.01. So what's our conclusion? We have sufficient evidence that's what's happening here. We have sufficient evidence that more men than women expect a pay raise or promotion. All right? Possibility of type 1 error. And of course, probability of type 1 error is 0.0013. Of type 1 error. Probability of type 1 error is the p-value, 0.0013. And that brings us to the end of that problem. Now, your textbook hardly deals with this next situation, but I just want to see if I could set it up quickly before my Apple Pen runs out. Okay? Which is essentially, what if we said that there's, we have a significant gap or a significant problem. If we can show that the difference between the proportion of men and women who believe that they will get promotion is more than 5%. What if we were interested in looking at that? Then in that case, we would test the hypothesis that, and then what happened is that if that is the case, the association could go on a campaign to try to get to have this issue dealt with. But let's just see if we have evidence that we could say the problem is actually quite serious if we can show that the gap is more than 5%. So basically we could say problem is serious versus the problem is not so serious, or the gap is not so serious. If that's the case, HOHA, then what would happen is we would say P1 minus P2 is greater than 0.05 versus P1 minus P2 is less than or equal to 0.05. So we basically have defined this as it's a serious problem if we can show that there's a gap of 5%, more than 5%. So in that situation now, P1 is not equal to P2. In which case, that's number one. Our test statistic would be Z P bar 1 minus P bar 2, that's P1 minus P2, over, and we'll just use the individual values. We have P bar 1 times 1 minus P bar 1 over N1, P bar 2, 1 minus P bar 2 over N2. Okay? That would be our test statistic. I'm trying to erase my pen, so bear with me. 3. So 3 is the decision rule. This is still a one-tailed test. We will actually keep alpha at, say, 1%. All right? Actually, let's just change alpha to 5%. All right? Let's change alpha to 5%. So if in that our decision rule, then in this case, so alpha is 0.05, in which case that has to be 1.645. That's our critical value. And so if Z is greater than equal to 1.645, we'll reject HO. Now step 4, the analysis very quickly before I run into a dead pen. So we have let's do that over here. 4, analysis. We would have Z is equal to the difference. The sample difference is still 0.15, but now the P1 minus P2 is 0.05. and we do the 0.52 times 0.48 over 200 plus 0.37 times 0.63 over 200. And when we work that out, it turns out that it is, the answer is 2.03. So the answer is 2.03. And as you could see, that 2.03 is larger than 1.645. Had I used a 1% significance level, it would be 2.33, and it would be my critical value, and then it would not be larger, so I would fail to reject. So let's do this. So p-value is equal to pz greater than or equal to 2.03. When we check that out, we have a p-value of 0.0212. So as you could see, it is smaller than 5%. But if we had done the test with a 1% significance level, then that would be larger than 1%, and we would fail to reject the null hypothesis. So step 5, decision conclusion. So since 2.03 is greater than 1.645, we will reject the null hypothesis. But we conclude we have sufficient evidence the issue is serious and merits attention. All right? And so we have a possibility of type 1 error. The risk of type 1 error in this case is 0.0212 or 2.12%. And if we decided that we wanted to change the significance level to 1%, then in that case we would fail to reject null hypothesis with a possibility of type 2 error. All right? So that kind of brings us to the end of the installment, part 4, which dealt with proportions. And with proportions, I want you to keep in mind that we have two possible scenarios. One possible scenario is where in the null hypothesis we claim that the difference between the proportions is 0. So if it's 0, it means that the two proportions are the same, in which case we now need a pooled sample proportion. We cannot estimate a single value with two different sample proportions, so we pool them together. If now we're not assuming that they're the same in the null hypothesis, such as the case I just dealt with there, that is, there's a difference between them that is non-zero, then we have to use a different test statistic. We call that case 2. On our formula sheet, we have case 1, where the difference between the proportions is 0, case 2, where the difference between the proportions is not 0. All right? And that brings us to the end of that. There are some other questions on the workbook that you could attempt, and they're quite similar in terms of the formulation and so on. The only thing that I've done is that I've actually just treated the problem as a hypothesis testing problem and then do all my 5 steps. The textbook or the questions tend to ask you to break it down into its parts. We'll ask you for the sample statistic, we'll ask you for a margin of error, we'll ask you for different things. But when you put it all together, a p-value, when you put it all together, it's really just getting you to do the 5 steps, but it's not actually referring to it as a 5-step process, right? Good. Thank you very much.